Question 1. From the perspective of electrical circuit design in HVAC systems, a technician is analyzing a circuit where multiple components are connected to the same two nodes. The technician notes that the voltage across each component remains the same, but the total current is the sum of individual branch currents. Which of the following best explains the nature of this configuration and the most appropriate application in an HVAC system? A. Series circuit configuration, used in overload protection for motors. B. Parallel circuit configuration, used in residential lighting circuits in control panels. C. Series parallel hybrid configuration, used in three-phase motor contactor control. D. Open circuit condition, used for temporary service lockout procedures. Answer. Correct answer, B. Explanation. This is the parallel circuit configuration where each component shares the same voltage but individual branch currents add up to the total current. In HVAC systems, parallel configurations are used in lighting circuits, control boards, and thermostat systems. They allow components to operate independently. In contrast, series circuits are used where failure of one component must stop the entire system. E.g., safety switches. The NEC National Electrical Code and NATE guidelines emphasize the importance of understanding parallel versus series design for safe and functional control circuits. An open circuit, by contrast, halts current completely and isn't an operational setup. Question 2. In light of recent developments in compressor technology, Mr. Alvarez is servicing a modern scroll-type air conditioning compressor. After replacing a failed capacitor, the unit still fails to start. He checks voltage at the terminals and finds adequate supply, but the compressor attempts to start and trips on thermal overload. What should Mr. Alvarez check next to accurately identify the issue? A. Inspect the start relay for sticking contacts. B. Check for reversed line voltage polarity. C. Verify if the system has improper refrigerant charge. D. Use a megameter to test for winding insulation breakdown. Answer. Correct answer, D. Explanation. The symptom, motor not starting and tripping thermal overload despite proper voltage, suggests possible winding insulation breakdown causing excessive current draw. Using megameter insulation tester is the industry standard to detect such issues per NATE diagnostic protocols. Checking refrigerant charge is unrelated to startup behavior. Reversed line polarity won't stop compressor function if L are both live in single-phase units. Start relay issues are more relevant to C-type motors, not scroll compressors which often use PSE or inverter-driven motors. Question 3. During the process of commissioning a new air-cooled condenser unit, Jenkins observes that the system pressures appear higher than normal ambient temperature. The airflow across the condenser appears weak, and she notes dust buildup on the fins. What is the most likely cause for the normal high head pressure? A. Undersized refrigerant lines. B. Restricted metering device. C. Dirty condenser coil. D. Low indoor airflow due to clogged filters. Answer. Correct answer, C. Explanation. Dirty condenser coils impede heat rejection, leading to high head pressure. The NATE air conditioning section emphasizes coil maintenance as part of routine service checks. Insufficient airflow across condenser fins causes poor condensation, which raises pressure on the high side, while restricted metering devices or indoor airflow issues affect evaporator side behavior. They don't explain high discharge pressure. Undersized refrigerant lines contribute to pressure drop but are unlikely to cause marked high head pressure unless severely misapplied. Question 4. With respect to airflow calculations, a technician must determine if the 3-ton split air conditioning system is receiving the appropriate airflow across the evaporator coil using a temperature rise method with a TAW electric heat strip and a measured temperature rise of 25 degrees. The technician calculates airflow using the equation CFA equals beta point AX dt CFM equals frac beta 1.8 times delta. CFA equals 1.8x dt BTU H. What is the correct airflow in CFM for this system? A. 370 CFM. B. 680 CFM. C. 925 CFM. D. 1100 cm. Answer. Correct answer, D. Explanation. First, convert the electric strip heater's power to BR to AWLs 34,120 BOAWLs 34,120 B2 equals 34,120 since UNAW equals 3,412 beta. CFA equals 341,201.83 million 12,027 1260 for EFMEM equals frac 34,120 1.8 times 25 approx frac 34,120 27 approx 1260 FIFMM equals 1.8x 2,734,120 1264 from rounded down slightly for losses and measurement errors 1100 CFM. Closest correct answer. This method is NATE endorsed for verifying airflow indirectly during commissioning. Proper airflow ensures efficiency and prevents coil freeze-up or high head pressure. Question 5. As demonstrated by Mr. Patel's repair on a rooftop unit, he replaces a failed run capacitor for a HESI condenser fan motor. After installation, he notices the motor is vibrating and operating at inconsistent speed. Which of the following best explains the cause of the issue and the correct response? A. Motor has a winding fault. Replace the motor. B. Capacitor rating is incorrect. Install one with proper MF value. C. System charge is incorrect. Adjust superheat and subcooling. D. Fan blade is bent. Adjust blade balance. Answer. Correct answer. B. Explanation. PSC motors rely on proper capacitor size in microfarads to maintain torque and stable operation. An incorrectly rated capacitor causes unstable speed and excessive vibration. NATE guidelines highlight proper capacitor matching as critical to motor longevity and system reliability. Winding faults would usually trip protection circuits. Fan blade imbalance would also cause vibration but not regularity. Refrigerant charge wouldn't affect motor behavior directly. Question 6. Taking into account the wiring configuration of a three-phase air conditioning system, a technician finds that the compressor is running backward. He has confirmed there are no start relays or capacitors in this system. What corrective action should be taken to resolve the issue? A. Reverse any two of the three-phase conductors. B. Add a start capacitor to correct rotation. C. Replace the motor with one with a higher torque rating. D. Reverse the polarity of the low voltage signal. Answer. Correct answer. A. Explanation. Reversing any two conductors in a three-phase system changes rotation direction, which resolves backward compressor operation. This is a standard NATE concept under three-phase motor theory. Capacitors are not used in three-phase motors. Reversing control signal polarity doesn't affect high-voltage power phase sequencing. This technique is especially relevant for scroll compressors, which can suffer damage if operated in reverse. Question 7. In an effort to improve indoor air quality, Simmons recommends installing a high MERV filter in a residential HVAC system. After the installation, the homeowner complains about reduced airflow and uneven cooling in some rooms. What is the most appropriate solution to balance filtration with system performance? A. Replace with a HEPA filter to increase efficiency. B. Increase fan speed to offset the pressure drop. C. Install an additional return duct to bypass airflow. D. Reduce thermostat set point to compensate. Answer. Correct answer. B. Explanation. High MERV filters create greater static pressure, which reduces airflow if the blower isn't adjusted accordingly. Increasing fan speed compensates for this drop. NATE training emphasizes understanding air resistance versus IAC. Installing a HEPA filter may worsen airflow due to even higher resistance. Duct modifications are more invasive and not the first step. Lowering the thermostat doesn't address airflow loss and stresses the system. Question 8. Examining the consequences of improper refrigerant charging, Mr. Franken is evaluating a system using R400 TINA. After topping off refrigerant based on pressure readings alone, the system exhibits high superheat and low suction pressure. What is the most likely reason for the system's current condition? A. The system is undercharged due to improper charging method. B. The compressor is failing due to thermal overload. C. The condenser coil is oversized for the application. D. The metering device is stuck closed. Answer. Correct answer. A. Explanation. Charging by pressure alone is unreliable without superheat or subcooling readings, especially in TSV or capillary systems. High superheat and low suction pressure indicate undercharging, which causes insufficient refrigerant reaching the evaporator. NATE mandates accurate charge using superheat, fixed orifice, or subcooling TSV per EPA Section 608 best practices. A stuck metering device. Failing compressor would show additional symptoms such as abnormally high head pressures or no cooling at all. Question 9. According to recent studies, the use of ECM electronically commutated motor blowers is increasing in high-efficiency systems. Is to raise replaces a failed PSC motor with an ECM blower in a residential unit but does not reprogram the control board. What problem is most likely to occur in this case? A. The blower will overheat due to mismatched power input. B. The system will function correctly without any issue. C. The blower speed will not match system airflow demands. D. The control board will reset to factory defaults. Answer. Correct answer. C. Explanation. ECM motors require programming or configuration to match airflow curves with system demands. Failing to do so results in mismatched speeds leading to poor dehumidification, noise, or inefficiency. NATE guidelines for system retrofits warn against assuming and plug-and-play with ECM motors. Power input is not the issue, as ECMs self-regulate voltage. The system won't default or reset the board, but will incorrectly if unconfigured. Question 10. The relationship between metering device selection and system performance is often overlooked. A technician replaces with a capillary tube to save costs. Over time, the system performance degrades, especially under varying load conditions. What is the primary technical disadvantage of using a capillary tube in this case? A. It requires more frequent filter replacement. B. It cannot adapt to changing load conditions. C. It operates with incompatible refrigerants. D. It causes excessive superheat during defrost. Answer. Correct answer. B. Explanation. Capillary tubes are fixed metering devices, meaning they don't adapt to changing heat loads like ESSVS. Under fluctuating ambient or indoor conditions, they fail to regulate superheat, leading to inefficiency. TSES per ASHRAE and NATE best practices are preferred for variable load systems. Filter frequency is not the issue, nor is refrigerant compatibility. Cap tubes can handle R22 and R400 TINA. Superheat during defrost isn't relevant in cooling-only cap tube applications. Question 11. In the context of electrical troubleshooting, Mr. Gomez is diagnosing a SE condenser fan motor that hums but does not start. The capacitor measures within the manufacturer's specifications and the motor windings show proper resistance. However, the motor shaft does not rotate freely when turned by hand. What should Mr. Gomez conclude and do next? A. The motor is seized mechanically. Replace the motor. B. The start capacitor is weak. Replace the capacitor. C. The control relay is faulty. Replace the relay. D. The power supply is low voltage. Check the breaker. Answer. Correct answer. A. Explanation. A humming motor that does not start paired with a mechanically stuck shaft indicates a seized motor bearing or internal mechanical failure. Even if electrical components test fine, a seized rotor prevents starting. According to NATE and NEC guidelines, this warrants motor replacement for safety and reliability. Weak capacitors cause failure to start, but with free shaft movement. Control relays or voltage supply issues would show different symptoms like no or no voltage at motor terminals. Question 12. Given the circumstances of an R400 TINA system with high head pressure and low suction pressure, a technician suspects a refrigerant restriction. After isolating the system, which of the following components is the most common cause of such a restriction and how should it be verified? A. Filter dryer clogged, verified by pressure drop across dryer. B. Compressor valve stuck, verified by amperage draw. C. Expansion valve stuck open, verified by temperature readings. D. Condenser coil dirty, verified by airflow measurement. Answer. Correct answer. A. Explanation. A clogged filter dryer restricts refrigerant flow, causing high head pressure and low suction pressure. Technicians use pressure gauges to check for a significant pressure drop across the dryer. NATE emphasizes verifying physical restrictions before replacing expensive components. Compressor valve issues generally cause high suction pressure or loud noises, while an expansion valve stuck open leads to low superheat and Condensers affect head pressure but less commonly suction pressure directly. Question 13. Considering the evidence from an HVAC startup report, Mr. Lin notes that the superheat value on a fixed orifice system is unusually low, yet the system is experiencing poor cooling and high energy consumption. What is the most plausible underlying cause of this issue? A. The evaporator coil is iced up due to airflow problems. B. The refrigerant charge is excessive, causing flooding of the evaporator. C. The compressor is underpowered for the system size. D. The condenser fan is not running, causing high head pressure. Answer. Correct answer. B. Explanation. Low superheat coupled with poor cooling and high energy use points to overcharging of refrigerant, causing liquid refrigerant flooding the evaporator. This reduces cooling efficiency and stresses the compressor. NATE and EPA Section 608 guidelines stress accurate charging to avoid overcharge or undercharge. Iced evaporators usually cause high superheat due to reduced refrigerant evaporation. Underpowered compressors affect capacity, not superheat. Condenser fan failure causes high head pressure but usually leads to high superheat. Question 14. Under the assumption that a technician is sizing ductwork for a new residential split system, which factor is most critical to ensure proper airflow and system efficiency according to industry best practices? A. Selecting duct diameter based solely on static pressure measurements. B. Designing duct runs to minimize total equivalent length and sharp turns. C. Using flexible duct material for all main trunk lines. D. Oversizing ductwork to reduce fan motor power consumption. Answer. Correct answer. B. Explanation. Minimizing total equivalent duct length and sharp bends reduces pressure loss, allowing more efficient airflow and reducing blow motor strain. NATE and ACAM Manual D guidelines recommend careful duct layout to avoid unnecessary restrictions. Relying solely on static pressure without layout optimization is incomplete. Flexible ducts are best used sparingly and not for main trunks due to increased resistance. Oversizing ducts can cause reduced velocity and poor air mixing, impairing system efficiency. Question 15. While examining the operation of a thermostatic expansion valve ESC, a technician observes fluctuating superheat during stable indoor conditions. The sensing bulb is correctly positioned and well insulated. What is the most likely cause of this superheat fluctuation? A. TSV bulb charge is lost or damaged. B. Improper refrigerant type is used. C. Thermostat wiring is faulty. D. Compressor suction line is leaking refrigerant. Answer. Correct answer. A. Explanation. A fluctuating superheat despite stable conditions and correct bulb placement usually indicates a loss or damage to the T6V bulb charge, impairing valve modulation. NATE training emphasizes proper TSV bulb maintenance is critical for precise superheat control. Refrigerant type mismatches would cause broader system issues. Faulty thermostat wiring affects system cycling but not superheater. Suction line leaks cause low refrigerant but not necessarily fluctuating superheat unless severe. Question 16. Throughout the course of performing planned maintenance, a technician replaces an air filter with one rated at MERV 16 in. A system originally designed for MERV 8 filters. The system is experiencing decreased airflow and high static pressure after the replacement. What is the best immediate solution to restore system balance without compromising air quality? A. Replace the blower motor with a higher horsepower unit. B. Downgrade the filter to a MERV 13 rating. C. Clean the evaporator coil and reinstall the filter. D. Increase the system fan speed if adjustable. Answer. Correct answer. D. Explanation. Increasing the fan speed compensates for higher static pressure caused by the denser MERV 16 filter, restoring airflow without sacrificing filtration efficiency. NATE encourages balancing airflow with filtration needs for indoor air quality and system performance. Replacing the motor may be costly and unnecessary. Downgrading filter sacrifices air quality. Cleaning coils is good practice but unrelated to pressure filters. Question 17. When faced with a scenario where a three-phase compressor motor's amperage draw is significantly higher than rated under normal operating conditions, which of the following is the most likely electrical cause? A. One leg of the power supply is open or missing. B. The condenser coil is dirty, causing system overload. C. The thermostat is set too low, causing short cycling. D. The blow-up motor capacitor has failed. Answer. Correct answer. A. Explanation. A missing or open leg in a three-phase power supply causes single phasing, which forces the motor to draw excess current to maintain torque, leading to overheating and failure. NATE electrical troubleshooting protocols prioritize checking power supply integrity for motor failures. Dirty coils cause mechanical overload, but not electrical imbalance. Thermostat settings and blower capacitors don't directly cause high temperature. Question 18. By evaluating the pressure-temperature relationship in a refrigerant system, a technician notes that the pressure is higher than expected for a given temperature on the low side. Which of the following could be causing this anomaly? A. Presence of non-condensable gases in the system. B. Evaporator coil is undersized for the application. C. Expansion valve is oversized. D. Refrigerant has been overcharged. Answer. Correct answer. A. Explanation. Non-condensable gases, like air trapped inside the refrigerant circuit, cause elevated pressures at given temperatures because they do not follow the vapor pressure curve of the refrigerant. NATE protocols emphasize proper evacuation and nitrogen purging to prevent this issue. Undersized coils cause low pressure and poor cooling. Oversized expansion valves increase refrigerant flow but don't cause pressure anomalies. Overcharging typically affects high side pressure more. Question 19. For the purpose of optimizing system efficiency, which of the following is the most effective strategy when troubleshooting? A variable speed blower motor on a residential system. A. Measure static pressure and adjust blower speed to maintain recommended CFM. B. Replace the blower motor with a SEMO for simplicity. C. Remove duct dampers to maximize airflow. D. Increase refrigerant charge to compensate for airflow. Answer. Correct answer. A. Explanation. Measuring static pressure and adjusting blower speed to achieve target airflow CFM is the best practice. NATE guidelines emphasize using static pressure as a direct indicator of system airflow and blower performance, especially with variable speed motors. Replacing ECM with PSC reduces efficiency. Removing dampers can cause uneven airflow. Increasing refrigerant charge does not compensate for poor airflow and may published. Question 20. Throughout the process of diagnosing no cooling complaints, a technician notes that the condenser fan motor runs normally, compressor starts and runs, but the system shows high superheat and low subcooling. What is the most likely cause of this symptom set? A. Undercharged refrigerant system. B. Restricted condenser coil airflow. C. Foot TXB causing overfeeding of refrigerant. D. Dirty evaporator coil restricting airflow. Answer. Correct answer. A. Explanation. High superheat and low subcooling indicate insufficient refrigerant in the system. Under charge, NATE recommends checking charge with superheat and subcooling values, not pressure alone. Restricted condenser airflow typically raises head pressure and subcooling. Foot TXV causing overfeeding would lower superheat. Dirty evaporator coil raises superheat but doesn't cause low subcooling. Question 21. Through careful analysis of a system exhibiting intermittent compressor short cycling, Mr. Lewis finds that the indoor thermostat is properly calibrated and the refrigerant charges within specification. However, the system's low pressure switch frequently trips. What is the most likely cause of this intermittent low pressure trip? A. Clogged or restricted air filters causing low evaporator airflow. B. Faulty compressor overload protector. C. Incorrect wiring of the low pressure switch. D. Thermostat anticipator setting too low. Answer. Correct answer. A. Explanation. Low evaporator airflow from clogged air filters or dirty coils reduces heat transfer, causing suction pressure to drop, which trips the low pressure switch. NATE emphasizes proper filter and coil maintenance to prevent such issues. A faulty overload protector affects compressor operation but wouldn't cause low pressure trips. Incorrect wiring or thermostat anticipator settings typically cause control issues, not pressure switch. Question 22. Considering the evidence of a failed motor winding during routine maintenance, a technician notices the motor has signs of overheating and insulation breakdown, despite correct voltage supply and no visible mechanical binding. What is the most probable cause of the motor failure? A. Voltage imbalance in the three-phase supply. B. Incorrect capacitor size causing current surge. C. Blocked condenser coil causing thermal overload. D. Low refrigerant charge causing compressor stress. Answer. Correct answer. A. Explanation. Voltage imbalance causes uneven current distribution in motor windings, resulting in overheating and insulation failure. Nate electrical theory stresses the importance of balanced supply voltage for motor longevity. Capacitor issues affect single-phase motors, not three-phase windings. Blocked condenser coils affect refrigerant systems but not motor windings directly. Low refrigerant causes compressor issues, motor winding failures. Question 23. In the absence of adequate refrigerant recovery equipment, Istishai is asked to evacuate the system prior to repair. He only has access to the standard vacuum pump rated for 500 microns. What is the best practice for evacuation in this scenario? A. Use the vacuum pump to reach 500 microns, then hold for 15 minutes to check for leaks. B. Use nitrogen purge in combination with vacuum pump to accelerate evacuation. C. Skip evacuation and proceed directly to recharge with refrigerant. D. Evacuate until the pressure reads 0 microns. Answer. Correct answer. B. Explanation. Nitrogen purge combined with a vacuum pump helps remove moisture and non-condensables faster and more thoroughly per EPA and NATE guidelines. Achieving 500 microns alone is acceptable, but purging expedites the process and improves system integrity. 0 microns is practically impossible and not required. Skipping evacuation violates environmental regulations and risks system damage. Question 24. As illustrated by recent field tests, a technician finds that a condenser fan motor running on a single-phase PSC motor experiences frequent starting failures and overheating during hot weather. What is the best solution to improve motor reliability? A. Replace with a SE motor of higher horsepower rating. B. Replace the PSC motor with a permanent split capacitor PSC motor with an appropriately sized start capacitor. C. Replace the PSC motor with the capacitor start capacitor run CSR motor. D. Install a crankcase heater on the compressor. Answer. Correct answer. C. Explanation. A CC Samoa has higher starting torque and better thermal performance, improving reliability under heavy loads like hot outdoor conditions. NATE standards recommend selecting motors with proper starting characteristics for specific loads. PSC motors have limited starting torque. Increasing horsepower without proper torque characteristics doesn't solve starting issues. Crankcase heaters prevent compressor flooding but affect fan motor startup. Question 25. With respect to system balancing, a technician is tasked with adjusting duct dampers to correct uneven airflow between rooms in a multi-zone residential system. The homeowner complains of some rooms being too cold while others are warm. What is the best initial step to correct this issue? A. Fully open all dampers to maximize total airflow. B. Adjust dampers to reduce airflow to colder rooms and increase airflow to warmer rooms. C. Seal return air ducts to balance pressure. D. Increase blower motor speed to force more air through all zones. Answer. Correct answer. B. Explanation. Balancing airflow involves reducing airflow to overcooled areas and increasing it to undercooled areas via dampers per ACAM Manual D and NATE duct design principles. Fully opening all dampers may exacerbate imbalance. Sealing return ducts disrupt system pressure and airflow. Increasing blower speed indiscriminately causes noise and energy inefficiency, worsening comfort. Question 26. From a practical standpoint, a technician finds an indoor blower motor capacitor that appears swollen and bulging but still measures capacitance within the acceptable range. What is the technician's best course of action? A. Leave the capacitor in service until it fails. B. Replace the capacitor immediately due to physical damage. C. Remeasure capacitance with different meter. D. Clean the capacitor terminals and retest. Answer. Correct answer. B. Explanation. A bulging or swollen capacitor is a sign of imminent failure regardless of current capacitance readings. NATE and safety standards require immediate replacement to prevent unexpected motor failures. Cleaning terminals or retesting doesn't address the physical damage. Leaving it in service risks system downtime and safety hazards. Question 27. When analyzing an air conditioning system equipped with an electronic expansion valve, EVE, ISTACHIM notices erratic superheat readings despite stable load and ambient conditions. Which of the following is the most likely cause? A. Incorrect control signal or wiring issue affecting the EVE actuator. B. Dirty air filters causing reduced evaporator airflow. C. Overcharged refrigerant leading to liquid floodback. D. Faulty thermostat sensor in the conditioned space. Answer. Correct answer, A. Explanation. EVE rely on correct electronic control signals for precise modulation. Erratic superheat often indicates control wiring faults or actuator malfunction, requiring electrical troubleshooting as per NATE standards. Dirty filters affect airflow but not EVE control signals. Overcharge and faulty thermostat sensors cause different symptom patterns but not erratic EVE operation. Question 20. To better understand the impact of refrigerant oil on system performance, a technician notes that excessive oil in the evaporator coil is causing diminished heat transfer and elevated superheat. What is the best method to correct this issue? A. Perform an oil change on the compressor and add a higher viscosity oil. B. Use an oil separator or accumulator to reduce oil migration. C. Increase refrigerant charge to compensate for reduced efficiency. D. Replace the evaporator coil with a larger unit. Answer. Correct answer, B. Explanation. An oil separator or accumulator prevents oil migration into the evaporator coil, maintaining efficient heat transfer and proper superheat. NATE best practices emphasize oil management to preserve system efficiency. Oil changes and viscosity adjustments affect compressor lubrication but not oil migration directly. Increasing charge or coil size doesn't solve oil fouling problems. Question 29. At the heart of this issue, Mr. Thompson observes that a system with a fixed orifice metering device experiences frequent coil freeze-ups during mild weather conditions. What adjustment or repair is most appropriate to prevent this? A. Install. E. Provide adaptive metering based on load. B. Increase refrigerant charge to reduce coil freeze. C. Clean the evaporator coil to improve airflow. D. Replace the condenser fan motor to improve head pressure. Answer. Correct answer, A. Explanation. Adds a refrigerant flow to match load conditions, preventing core flooding and freezing, which fixed orifice devices cannot do. NATE guidelines suggest TSVS for systems exposed to varying loads or mild conditions to optimize performance and avoid freeze-ups. Increasing refrigerant charge worsens freeze. Core cleaning and fan motor replacement address other symptoms but not metering adaptation. Question 30. In terms of refrigerant handling, a technician discovers that a unit previously charged with R22 has been retrofitted to use R400 TINA without changing the oil type. What is the most significant consequence of this oversight? A. Compressor failure due to oil incompatibility with R400 TINA. B. Increased refrigerant pressure causing system leaks. C. Reduced cooling capacity due to incorrect refrigerant volume. D. Electrical overload due to motor inefficiency. Answer. Correct answer, A. Explanation. R400 TINA requires POIL, which is incompatible with the mineral oil used in R22 systems. Failure to change oil leads to poor lubrication and compressor failure. NATE and EPA guidelines mandate proper oil changes during retrofit to prevent damage. Increased pressure, refrigerant volume, or electrical overload are secondary issues but not direct results of oil incompatibility.